In this lecture, we're going to go over how to retrieve thermodynamic properties. So where do we get all those properties from? For water, they're called our steam tables, and table A4 is our superheated vapor tables. Table A5 are our compressed liquid tables, and table A2 and A3 are our two-phase liquid vapor tables. So as an example, we're going to look at, here's table A4. If you remember, in single phase regions, we can fix our state by temperature and pressure. So a few things to note, this is two little separate tables here. We have temperature, specific volume, internal energy, enthalpy, and entropy. For right now, we're really going to only look at the first three columns. So the other things you have are, here is your pressure for its table. So this whole left side is for a pressure of 1 psi, and this side is for a pressure of 5 psi. So say I'm trying to fix a state at 1 psi and 250 degrees Fahrenheit. I'd come down here to 250 degrees Fahrenheit, and here's my information. So my specific volume would be 422.4 cubic feet per pound. There's tables in both English units and SI units. So what happens if you're looking for an entry in your tables and it's not there? Well, it's in the case where you're going to have to use linear interpolation. Well, linear interpolation is based on the slope of a straight line. So here's my point x1, here's my point x2. I have a y1 and a y2. If I connect them with a straight line, I can put in a point in the middle called xy. Well, the slope of my line is equal to y2 minus y1 over x2 minus x1, which is also equal to y minus y1 over x minus x1. For example, if I was looking at 10 bar and I wanted a temperature of 215 degrees Celsius, I want to find out that 215 degrees Celsius doesn't exist, but I have a table, I do have an entry for 200 and 240. So I could say that I have my specific volume at 240 minus my specific volume at 200 divided by 240 minus 200 is equal to the specific volume that I'm looking for minus the specific volume at 200 divided by the temperature at which I want my answer and the temperature of my lower bound. If I do that, I'm going to find out that my specific volume is 0.2141 meters cubed per kilogram. Let's look at a quick problem. Here's example 3.1. We have a vertical piston cylinder assembly containing 0.1 pounds of ammonia, initially a saturated vapor. It's placed on a hot plate. Due to the weight of the pistons and the surrounding atmospheric pressure, the pressure of the ammonia is 20 psi. Heating occurs slowly and the ammonia expands at constant pressure until a final temperature is 77 degrees Fahrenheit. We want to find the volume occupied by the ammonia at each end state and the work for the process. It also asks us to draw some TV and PV diagrams. So here's a TV diagram. I'm going to draw my line of constant pressure. It says it starts initially at saturated vapor. That means I'm at the edge of my dome. So there's 0.1. I add heat until I'm at 0.2. If I look at it on a PV diagram, again, I'm going to draw my dome. I'm going to draw 2 lines of constant temperature because my temperature clearly changes from state 1 to state 2. Here's state 1, here's state 2. So let's look at state 1. We have saturated vapor. And this is ammonia. So my temperature state 1 is equal to my saturation temperature at 20 psi. So if I go to table A15E, because there's tables for various substances, I'm going to find that T1 is equal to minus 13.63 degrees Fahrenheit, and V1 is equal to Vg, which is equal to 13.497. And where did I find this information? This is actually a snippet of A15E. The top of every table, when it tells you your pressure that the table is listed for, it actually tells you your saturation temperature. And the first line of the table is also your saturation properties. So then we need state 2. So state 2 is P is equal to 20 psi, again, because our pressure is constant, and our temperature is equal to 77 degrees Fahrenheit. So again, I'm going to look at this same table, and we're going to need to interpolate between 70 and 80 degrees Fahrenheit, where this is 70 and this is 80 and this is 70. Sorry, my snipping cut off the temperatures. So that's going to be 16.765 minus 16.436 divided by 80 minus 70, which is going to be V2 minus 16.436 over 77 minus 70. My specific volume at state 2 is 16.7 feet cubed per pound. So my volume at state 2 is my mass times my specific volume, which is my 0.1 pound times 16.7 feet cubed per pound. So my volume at state 2 is 1.67 feet cubed. And the last part it asks for is our work. Our work is equal to the integral of P dV, which is equal to P times V2 minus V1, which is equal to 20 psi times 1.67 minus 1.35 feet cubed times 144 inches squared per foot squared times 1 BTU is 778 foot-pounds. So my work is 1.18 BTUs. Well, that's how you use the superheated vapor tables. In the next video, I'm actually going to show you how to use the saturated tables.